Okie dokie. So, welcome to another fun filled day of physics. We're going to pretty much pick up where we left off and keep talking sound. Talk about some of the other things about sound, like sound intensity, um, things like the Doppler effect, what happens when we get sonic booms. Basically, today is just going to be talking about all the sorts of weird stuff with sound that we either take for granted or that happen that we don't realize happens and what's going on there. But before we get to new stuff, anything from before that we have questions about? Feeling okay in general with the idea of sound waves and how they work? Okay, I will take that as all is good. Thanks for the thumbs up there, Max. All right, so we're going to continue talking about sound, and I want to revisit speed of sound. Um, so I kind of gave you the overview of how it's all about the bulk modulus and the mass density, but you can actually look at it from a chemistry kind of viewpoint, looking at ideal gases, and it gives us kind of a better feel for what kind of speed we'd get when we're talking about sound and air, and we can see how it's related to some of the other quantities that may surprise you. So let's do this. Let's go to the board and let's talk a little bit more about sound. All right. So let's look at this from like the ideal gas law kind of idea. Now, we're going to learn more about this in a little bit later this quarter when we start talking thermodynamics. Um, Thermodynamics, just so you know kind of where we are today, we're going to finish talking about sound. And then we're going to move to the last portion of this class, which is thermodynamics. And that's going to be looking at how, thermo is heat, dynamic means move. So it's all about how heat moves, how energy moves with heat and all that. And one of the things we will talk about is gases and why they behave the way they do. But basically what we can do is we can look at the ideal gas law. And I don't know if you've seen this before, but the ideal gas law basically shows you a relationship between pressure, volume, and temperature of gas. And it looks like this. We have PV is equal to nRT. Now, in here, just for those of you who've never seen this, because some of you may not have ever taken chemistry, I don't really know all your background. So these different quantities, the P is pressure, and immediately you can see why we're going to use this when we talk about waves, because sound waves are pressure waves, so it does depend on the pressure. Okay, so we know this. The V, this is volume. The T, this is your temperature. And this temperature is in Kelvin. If you're not familiar with Kelvin, I'll explain what that is in a minute. So this is temperature. And then the N and the R, these, the N is the number of moles. So it's basically the amount of the gas. And then R, it's a constant. It's called the ideal gas constant. So R is just a constant. And then N is the number of moles. So just think of that, it's an amount. It's the amount of gas.
Which R are we going to use?
So this is the, well, it turns out we're not going to actually use the R.
Okay.
We're going to incorporate that in to when we simplify our formula.
Okay.
Okay, so, but this is the big R as opposed to the little r. I don't remember what their names are. I think this one is the I think this is the ideal gas law constant, I think is the name of it. But I do know that we designate them as either big R or little r. Okay, now this is great and all, but I want to start getting it into terms of other things that are more physics. So like the number of moles isn't super useful. Instead, what we're going to do is we're going to look at the number of moles as a mass idea. And what this is going to be, we're going to write this as little m over big M. And the little m is the mass, right? And then the big M is the molar mass. Okay, so anyway, we've got this. So molar mass is kilograms per mole, basically. So if we replace that in, that changes this formula a little bit. We now have PV equals little m over big M times RT. And I'm going to go ahead and divide by the volume just to get pressure by itself. And I want you to notice that this gives us now mass per volume, which is a density. So basically, you can determine what the pressure of a gas is if you know its density, you know its temperature, and you know its molar mass. And molar mass is really going to come from what it's made out of. Okay, so what I want to do now is I want to look at how this changes with density. Because that's what velocity is. Velocity is really looking at, it's related to the change in position or pressure, sorry, with density. Let me show you, let's kind of fill this in. If we go back to the idea of this chunk of air that's moving, we know that that volume that's moving, it takes a certain mass to cause that, or sorry, a certain force to cause that, right? So here's this little chunk of gas that's going to be moving. Okay, so our sound wave is going to be going through here. And kind of like I was showing you last time in our little derivation, what we see is that if you were to take the density times the area, so that's going to give you a mass times velocity. This is momentum. And what we know is that this same, or it's not momentum, it's the amount coming through, because the velocity is that area times velocity gives you a volume, and then times gamma is your mass. So this mass that goes in has to be the same as the mass that comes out. So remember what we did is we extended it a little bit. I think in my picture I drew it circular, like as a pipe, but this is rectangular. It's the same kind of idea. What we're going to get is that this is actually equal to rho plus d rho, if we allow for a slight change in our density, times A times V plus dV, a slight change in our velocity. So just think of this as, if we have a change in density, there has to be a corresponding change in velocity, or vice versa. If there's a change in velocity, there has to be a corresponding change in density. So those areas don't matter. They just kind of cancel out. If we distribute through, what you'll see is we get rho V is equal to rho V plus VD rho plus rho dV plus d rho dV. So I just FOILed it. I am going to be able to cancel those rho V's. Those guys go away. And this last bit is super small. And I apologize for getting really technical here, but that's super small. You may remember in Calc 1 when we talked about differentials, we basically just ever said if you have a differential times another, it kind of goes away. Okay, well, that means that these two things have to add up to 0, which means we can kind of rewrite this as rho over d rho is equal to minus v, or no, I don't want it that way, d rho over rho equal to minus v over, or minus dv over v. So we're going to come back to the ideal gas law in a minute. Okay, so we know we have this. If you look at a force kind of idea here, if we just look at the forces acting on this block, we're going to get a change in pressure, and we know that the force that is being applied here, there's the pressure in each side, right? And so the net force is the difference in those pressures. So let me go ahead and write this. So our net force, it's going to be the pressure times the area minus the pressure times the area of the other one. So if this is a little tiny chunk, our pressures are going to be, or our force is going to be pressure times area. So we'll make it say dy and dz. So y will be in and out of the board, z will be up and down. That's dy dz. And then the other one is going to be P plus delta P, whatever our change in pressure is. Again, times that dy dz. So if we make this really, really small, this net force, which is going to be mass times acceleration, is going to be minus dp dy dz. Because when you distribute, the part with the p cancels with this because it's being subtracted. And then the delta p, I just made it a little d, made it really tiny. All right, now what I'm going to do here is I'm basically going to link these two together because I know my acceleration is dv dt. I'm going to divide by mass at the same time. So we're going to get dv dt is equal to minus dp dy dz over the mass. And the mass is just the density times the volume of this. So we're going to get a minus dp dy dz over rho times dx dy dz. And all kinds of stuff cancels, the dy's and the dz's. So let me bring this back up to the top. We've got dv dt. That's going to equal minus dp over rho dx. And if I multiply by the dt, I get dv is minus dp over rho times dt over dx. And dt over dx, that's just 1 over your velocity. So we get dv is equal to minus dp over rho times 1 over v. So if I just get rid of that fraction, I've got rho v times dv is equal to minus dp. And we're really close to being done with what I want to show you here, because now I can integrate this. You remember separable differential equations? Pretty sure you saw that last quarter in physics or in calculus, where if we get all of our variables separated, we can go ahead and integrate both sides. Realize that rho is constant, the density of this fluid we're assuming is constant. So if we integrate, what we end up getting is rho times v squared over 2 is equal to negative p, right? And so we could go ahead and put a plus c or something, but we can assume that it's 0. And then so solving for v, we end up getting actually, hold on, I totally botched where I wanted to go with this. We have rho times v times dv. Yeah, hold on a second. I wanted this in terms of something. So we had rho times v times dv is equal to minus dp. So from the continuity equation, I put that up just a little bit ago. Do you remember there was that thing about rho dv plus vd rho equals 0? If you don't remember that, we had that. It was rho dv plus vd rho equals 0. Let me get this, change this. You notice I've got a rho dv. I'm going to change that to vd rho. So it's actually a negative v times vd rho is equal to minus dp. So the minus signs cancel, and I get that v is the square root of dp d rho. Okay, so now we're going to go back to the ideal gas law. Because the ideal gas law, if you remember, we were able to write it as P in terms of rho, right? We had P was equal to and we had rho times RT over M. And so we can go ahead and differentiate that to get our dP d rho. And so what we end up getting, if we put that in here, is that V, it's actually equal to the square root of RT over M. And so since R and M are fixed, R is a constant, M is according to whatever the gas is, I just want you to notice that this is some multiple, I'm going to call it K, times the square root of T. And here's kind of the end result of this, what I want you to see, is that this is our speed. The speed of sound in your medium is dependent upon the medium. That's what the K is. The K, this is going to be determined by the gas. So if we've got, say, nitrogen, which our atmosphere is primarily, so whether we've got that or oxygen or helium or, that's going to change our K because it involves our molar mass and some other stuff. But not only that, it depends on the temperature. So if you change the temperature of the gas, you're going to change the speed of sound in it.
So you're telling me that sound travels differently in the winter than in the summer?
I'm absolutely telling you that. Yep.
That's wild.
So if it's a hot day versus a cold day, the sound is going to travel at a different speed. Yeah. So there's a lot to it. There's actually quite a bit to how we figure out what the speed of sound is. And so that number that I told you before, what was it? I forget what I told you, the speed of sound in air. 343, 334, whatever. That's actually determined for a specific temperature. Okay, so when we talk about the speed of sound, we bring up like the word like Mach 1 would be the speed of sound. Mach 2 is 2 times that. It's usually based at 1 atmospheric pressure at 20 degrees Celsius. That's kind of the standard, 20 degrees C. But yeah, you change the temperature and the sound changes. So for example, and I know that this is kind of a weird thing, but let me go to my other screen. So both of my kids were in marching band. Like it was one of the things they like to do. And my older son played trumpet. And in the marching band, when it got really cold, because they'd be playing, at football games, in the fall, it was quite chilly out there. And it caused them to go out of tune. Two things happened. One, and we haven't talked about this yet, but temperature will change the length of things. When you heat them up, they lengthen. When you cool them off, they shrink. We'll talk about that in thermodynamics. But one thing that happened was the actual length of pipe in the trumpet changed. And as we saw last time, you change the length of a pipe, you change the fundamental frequency, so you'll change the sound that comes out. So that happens, but also the air was colder. And because of that, the sound traveled differently. And because the sound traveled differently, different speeds, it messed them up. When they were far apart from each other on the field, it's not, sounds are arriving at slightly different times. So now they're playing a little bit off of what they normally do, and it wouldn't sound as good. So that was one of the things that they would have to try to take into account. So weird for sure, but it does change. The speed of sound does change depending on the temperature. All right, so it's a little bit more complicated than I made it seem last time. And even this is kind of simplified. You start messing around with the kinds of gas, and they behave differently. And when I say different kinds, it's really their molecular structure. If you have something that's a diatomic, that just means there are two atoms that are stuck together like oxygen. Oxygen in the air is O2, and so it's two oxygens. You can kind of think they're attached kind of like a barbell. What they do is completely different than if you have something that's monatomic. The monatomic would be like helium. Helium can just exist, He, right? That's going to do something different versus something like polyatomic, like CO2, carbon dioxide. And so you start adjusting those, and even what I showed you here gets more complicated, right? So we'll definitely talk more about that when we get to thermodynamics and we talk about the theory of gas. So we'll bring this back, and I'll say something like, hey, remember when? And I'll say, yeah, when we did that, we didn't take into account gamma. You'll know what I mean when I say that later. Okay, so anyway, so there's a little bit more about the speed of sound. It's not quite as simple as you think. And I know it already wasn't that simple, but it gets pretty complex. All right, so the next thing I want to talk about is sound intensity. Like when we talk about sound, how loud something is, we're really trying to get at intensity. And you guys have probably all heard of the unit of measurement called a decibel, which is a measure of how loud something is. Well, let's talk about that. Let's talk about what decibels are, and let's talk about sound intensity just in general. So I'm going to go back to the board. And let's just start with the idea of intensity.
Real quick before you erase, what does that
Yeah,
say
sure.
at the bottom in green? Determined by what?
Gas
Gas.
is like the
Thank you.
type of gas. So that constant, whatever that K is, that's where we'd have to know, oh, we're talking about traveling in hydrogen or nitrogen, or even if we go to the air, our atmosphere, we'd have to look at the breakdown of nitrogen versus oxygen versus water vapor versus everything else.
Okay, thank you.
Yeah, you're welcome. Okay, so when we talk about how loud a sound is, it's really looking at how much pressure differential is going on. Since sound is a pressure wave, we're really looking at like a loud sound. That just means there's a huge pressure difference. So here's how we're going to define intensity. Sound intensity, we're going to look at how much power are we getting over a given area. So this pressure wave is going to be carrying energy. We're going to look at how much energy is being transferred in a certain amount of time. And then we're going to divide it by the area, the cross-sectional area that this wave is hitting. Because if I were to concentrate all of the energy, let's say I've got a certain amount of energy, and I were to concentrate it over this square, there's going to be a very different effect than if I were to concentrate that energy over the entire whiteboard. So there has to be some sort of an area idea here. Okay, so we're going to be looking at basically how much power happens over a given area. Okay, now we already know that it's a wave, which means instead of looking at the power at at any one particular point, we're going to look at the power averaged over one cycle. Okay, so when we do the power here, power for a sound wave, when we say power, what we're really going to do is let's look at a average timed average value. Because we've already seen that in the function, in the equation for a wave, remember it's got an x and an omega, or an x to the t, right? So we have our wave called y, so is equal to a cosine of kx minus omega t. I'm not going to bother with a phi, but so it depends on position and time. So what we're going to do is we're going to just average this over one cycle. So that will make things just a little bit easier for us, and it makes more sense than some sort of an instantaneous power, because power is always over a certain amount of time, and so since it's changing, it's kind of the same idea as looking over just one wavelength and going, okay, here's what's going on in general. All right, so if you do that, if you look at the power, and then you look at the area and everything, it turns out, and I'm going to just save us the time. I know you don't really care about the derivation, plus I just turned your brain into Swiss cheese by looking at the derivation for speed relative to temperature. But what we're going to find for this is that it's actually the square of the amplitude. So if you remember the delta P max, what we found for sound waves, was that delta P, that was actually the amplitude of our wave. So it's that amplitude squared over 2 rho times V. So where the rho comes in, why the rho and the V come in, is if you look at power, remember it's a force per time, and force is a mass times acceleration, and mass has in it the rho. The acceleration leads to the V. But again, if you're curious, I will show you where all that stuff comes from in like an office hour or something like that.
What is that? Delta P
Go ahead,
mass?
say again.
Is that delta P mass?
Max.
Max. Okay.
So just think of this. This is the amplitude of the sound wave.
Okay.
So we're squaring the amplitude. So it's the pressure amplitude, right? Remember what's going on. Those particles, they're going back and forth, right? And this delta P max that's the maximum pressure that this sound wave is producing. So that's why it's the amplitude.
Okay, thank you. That makes sense.
Yeah. So check out what happens then. If we increase the amplitude, then we increase the intensity. And that should make total sense because increased amplitude means louder. What you could think of as louder is greater amplitude. So if we have a louder sound, it's going to be more intense. And if it's quieter, it's less intense. Okay, so then let's look down here. We've got the 2 rho and the V. So rho is your density. So if your density increases, then your intensity is going to decrease. Does that make sense? Can you reason that out? Because think about it, if it's more dense, it takes more energy to move it, to move the actual particles. And so the energy that you've got in this wave, more of it's going to be used to move things. So it's not going to be as intense. And then the same thing happens here with our V. If we increase V, if we increase the speed, the intensity goes down. And this one probably feels a little bit weird because that one is like, but wait a minute, if it has a faster speed, it should be like hitting us more. But remember that this power, it's a time averaged. And if the wave is coming by you really fast, it doesn't have a lot of time that it's interacting with you. And so since power requires time as well, we've really eliminated how much time it has to impact. Anyway, so if you just go through the derivation using the wave equation, we find out that this is what our intensity is. Now, the measurement that we use are decibels. Okay, so decibels are the unit of measurement that we use for sound intensity. We have different units for different kinds of intensity, but for sound intensity, it's the decibel, right? It's in decibels. The units, decibels are dB, are the letters that we use for them. And decibels, these are unitless. So there are no units on it. but this you should have a problem with. Because if we look at how intensity was defined, remember it was power per area. So that means that the units on this are watts per square meter. And if we're going to use something that doesn't have units to describe something that does have units, we should probably be a little concerned. However, that's done other places. A good example is earthquakes, right? When we have an earthquake happen like that one that happened in the middle of Nevada just last week or whatever, the units that we use there, or what we use there is the Richter scale, right? So we say that that was like a 6.5 on the Richter scale. That 6.5 is a measure of intensity, but it's also dimensionless, where actual intensity of a earthquake should be in some sort of units. Well, that's because decibels, the decibel number comes from comparing the intensity of a given sound to the intensity of a baseline number. Okay, so this is how we actually calculate decibels. So we use beta to show this is how we calculate the decibels. It's actually going to be 10 times the log of our intensity I divided by I naught. And I naught, that's just a reference level intensity. It's chosen, it's a specific amount. I naught is actually equal to 10 to the minus 12 watts per square meter. Minus 12. So when we get a decibel number, that number is actually what pops out of this formula. So think about it this way. If our intensity was I naught, those two numbers are the same. So we'd get 1. The log of 1 is 0. So basically, this is the sound level that corresponds to 0 decibels. So on the hearing, or on the sound intensity scale, 0 decibels means this intensity. So if you're curious where this came from, and you probably are knowing this group, this is basically the lower limit of hearing. Different people have different lower limits, obviously, but this is historically the lower level, the lower limit of actually being able to hear. So you'd have to have an intensity of this much for your eardrum to actually be able to register it and then send it as some sort of a signal to your brain. So it is actually possible to have negative decibels, but negative decibels would mean you can't hear. Okay, so let's look at just some numbers and see what that does in terms of our intensity. So just kind of regular old conversation. Like if you and I are just talking to each other with normal kind of voice, we're not yelling at each other. A normal conversation, it has a intensity on the order of 10 to the minus 6. So I don't know if you know this symbol using the little alpha here. If you've not seen that before, that just means that it's on that order, on the order of 10 to the minus 6. So our conversation may actually be 5 times 10 to the minus 6 or 8.3 times 10 to the minus 6 or whatever, but a conversation is usually at that kind of level. So let's see what that decibel number would be. So the corresponding decibel to a level for a conversation is going to be 10 times the log of 10 to the minus 6 over 10 to the minus 12. And here you can see why the units go away. Because when we take I and I naught, they both have the same units, those cancel, and we're left with just a plain old number. Okay, well, doing this division, we get 10 to the 6. The log of 10 to the 6 is 6. We get 10 times 6, or 60. So just good old having a regular conversation. We have a decibel level of 60. All right, well, let's look at like a rock concert. So we're going to go to a rock concert. We're going to be up nice and close to the speakers, right? Because if it's too loud, then you're too old. So let's say that what we're getting there is an intensity on the order of 1. No, I'll tell you, let's do this. Let's see. If we were to look on a decibel scale, let's just see what doubling the decibel level does. Okay, so let's say that we've got a decibel level of 120. Let's see what the I is. Let's compare that to this conversation. Okay, so if the decibel level is 120, we're going to get 120 is equal to 10 log of I over 10 to the minus 12. So we get 12 is equal to log of I over 10 to the minus 12. We want to solve that for I. We got to convert this to exponential. So we get 10 to the 12 equals I over 10 to the minus 12. And that tells us that that I is on the order of 10 to the 24. Okay, so check this out. All we did was we doubled the decibel level, but look at the increase in the power, the intensity. The intensity goes from 10 to the minus 6 to 10 to the 24. Oh, I totally botched that. It's not 24. It's 10 to the first. I can't do simple math today. It's 10 to the 0. This is around 1. It turns out that 12 minus 12 is 0, not 24. Fun fact. All right. So we doubled our decibel level, but we increased our intensity by a factor of 1,000,000. 1,000,000. So this scale is really deceptive, because every time you increase by 10 on the decibel scale, you increase the intensity by a factor of 10. So we went up 60. That means we had to increase by 10 times 10 times 10 times 10 times. So we had 6 of them, or 1,000,000 times as loud or as intense. So when you're at a really loud concert or something and you're getting a decibel level of like 120, this is why it hurts after one of those concerts. I'm sure you guys have experienced that, right? You leave, your ears are just ringing like crazy. but it, like, you can physically feel pain. And this is one of the reasons. So anyway, that's how decibel levels work. So just be aware of that, that an increase in 10 in your decibel is actually a multiply by 10 in the intensity. So it's a logarithmic scale, and that's why that happens. You know, I was talking about the Richter scale. It's also logarithmic, so similar stuff will happen. Where when you increase the Richter scale number by 1, it is actually 10 times as strong. pH scale is also logarithmic. We have lots of logarithmic scales. But the one other thing I definitely want to point out is recognize that this is base 10 log. I know in math class, in calculus, we tend to get really lazy and just say log, and that means natural log. But here, I mean log, base 10 log. All right, so there's a little bit about intensity. So this is a good place to take a break. Let's take 10. Let me pause the recording. Okay, so there are really like 3 more things I want to talk about, 3 general things. One, I want to talk about the Doppler effect. And the Doppler effect is how sound changes when you have moving, either moving source of sound or you yourself are moving. I want to talk about shock waves that come from sound, like when we break the speed of sound, sonic boom. And I also want to talk a little bit more about interference, some of the things that happen with interference. So we kind of have those 3 general topics that we're going to use, talk about today and kind of finish out. So I think I want to start with the Doppler effect, because the Doppler effect is kind of cool. And it's something that we experience all the time. So for example, if you've ever watched, say, like a car race on TV, or you've actually been at one, and you hear the cars go by and you hear the right, you hear that sound change as it passes, or an ambulance that's going by, you hear a certain sound, but as they move away, the pitch changes, you hear a different sound. So that's the Doppler effect. And what's really going on there is you're hearing a change in frequency, right? We've already kind of talked about that sounds we hear, the loudness is amplitude. It's the that maximum pressure. But the sound we hear, the actual note we hear, is frequency. And so different frequencies produce different sounds. Like, remember when I was like blowing across the bottle and we heard different pitches? Same kind of thing. So you hear a different pitch, that means frequency is changing. So when the Doppler effect is going on, when that race car goes by us, we're hearing a change in frequency. Now, this is a perception thing. The frequency actually isn't changing, the frequency of the sound. Or you think about like a siren that's going. When a siren's going, it's got set frequency, set sound. As it goes past us, it just seems like it changed. And that's what the Doppler effect is. So let's go to the board and let's see how Doppler effect plays out. But it looks like, Bradley, you might have a question.
How did you know the unmute button?
I saw the mute thing turn.
Yeah. Isn't it, correct me if I'm wrong, but when like astronomers or astrophysicists are observing orbiting celestial bodies, they use the Doppler effect to determine certain things about it?
They do, yeah. And the Doppler effect works for other waves as well. And what they use in astronomy is they're looking at the light, and they're looking at the change in the frequency of the light. And just a little, might as well just tell you this. Again, it's probably going to be a spoiler with me. I don't know that we've actually set who's teaching what, but it's usually me. So light, the frequency of light is its color. So when we see red light versus blue light versus green light, that's a different frequency of light that we're seeing. And so the Doppler effect, what it'll do is it will change the frequency so that the color changes a little bit. So if you have an object, let's say that's shining a red laser, okay, so you're seeing red, if it moves in the right way, it will make it so that that red doesn't look red anymore. It looks more orange. Okay. You could also go the other direction where now you wouldn't see it anymore because now it's infrared. But basically, it can shift one way or the other. And so the terminology that we use in astronomy is redshift and blue shift. And redshift is just saying that the frequencies are moving so that they're closer to the red end of the spectrum. And blue shift means they're moving towards the blue end of the spectrum. But yes, you are correct that they do use the Doppler effect to really determine which direction things are moving. That's how we know like the universe is expanding. Is good. By looking at stars, we know what colors we should see, but we're not seeing exactly those colors. We're seeing them shifted a little bit, and you can use Doppler, what we're going to talk about right here, to figure out how fast they're moving, or at least how fast they're moving relative to us. So
Wild.
yeah, it is. It's pretty cool. And then don't get me started about relativity and color, because that changes stuff too, but that's for next year. All right, so let's go to the board and let's talk Doppler effect and what's causing it, why we see it, and how it actually changes the frequencies. All right, so here's what we're going to do. Let's look at having some sort of a source of sound that's going to be moving, and we as observers are going to be stationary. Okay, so we're just going to be sitting put, and this thing that is producing sound is going to be moving. All right, so here's going to be us. So here we are watching the Indy 500, getting our beer on, enjoying the race. Oh, and by the way, so I went to school in Indiana, really close to Indianapolis. My dad actually grew up about a mile from the track, so I know quite a bit about it. And really, the only point of going to Indy 500 is to drink beer. People get just loaded, because otherwise, why watch cars go around in a circle? Anyway, so here we are, we're watching, and let's say there's a source of sound. There'll be our race car, and our race car is going to be coming in this direction. Okay, now, if that race car was stationary, let's actually erase this arrow for a second. So the race car is stationary, but is producing a sound. So it means it's going to be creating a sound wave with a given frequency, and those waves are going to come out from the car with a given frequency. So I'm going to show this as having the same wavelength. So these are wave fronts. So remember how when there's a sound, it's coming out as a sphere. This is the part of the sphere that's closest to us. But the gap between all of these is exactly the same. So that's the wavelength, which is giving us whatever the frequency is. Okay, so cool. So what we hear is these waves coming at that certain frequency. All right, well now let's put this guy into motion. So let's just think about, at this moment, we produce a sound wave. And so that sound wave, let's say a little bit later, shows up here. Well, what happens now is we're going to see those waves start kind of bunching up on each other. Because think about this. So here's the car moving towards us now. So it sends out the first wave. Now, by the time it's ready to send out the second wave, the car has moved forward, right? So let's just think about this as the distance from the car to the wave. We'll just use the front, is that distance right there. So before, while it was stationary, the sound wave would reach this far before the next one came. And then those would move, and the next one would come, and those would move, the next would come, and so on. But now that next sound wave is actually going to start closer to this guy because we're making up some of the speed, some of that distance that the wave is traveling. So if that race car is moving towards us, what we're going to see is that that wavelength has shrunk. And again, that's because some of the distance that this sound was traveling before relative to the car is going away because the car is moving in the same direction. And the closer that the car is traveling to the speed of sound, the closer these waves are going to come. So if it's traveling really fast, it's going to cause a big shrink in that wavelength. If it's going slowly, it's going to be a small shrink. But regardless, as it's moving towards us, it's decreasing the wavelength. So what we're going to see in this instance is we're going to see a smaller wavelength. All right, so that's if the car's moving towards us. Now, what if the car is moving away from us?
It's going to be bigger.
Yeah, it's going to cause an increase for kind of the same reason. Now, this distance is how far the sound would have traveled in that time, but we're going to add to it whatever distance the car is moving in the other direction. So in that situation, what we're going to see here are bigger wavelengths. So here we're going to see bigger lambda because we're moving the other way. All right, so this is what's going on with the Doppler effect. We're seeing a now difference in wavelength. So let's see if we can do the formula on it, or do some math on it so we can get a formula to show us what that actual change in wavelength and therefore change in frequency happens to be. Okay, so let's just think about the stationary case. And so that's going to have a given frequency and a given wavelength. And let's just talk about wavelength, and then we'll relate it to frequency in a second. Well, no, let's just do the whole thing. So the way that we get frequency from wavelength and vice versa is by looking at the speed of sound, right? The speed of the wave. So what we know is that wavelength in general, wavelength times frequency equals the speed. So when I say V here, that's not the speed of the car, not the speed of the source, that's the speed of the wave. So in this case, the speed of sound in air. All right, so in this case, in the car is stationary case, the lambda we're going to see is V over F, right? Or the frequency alternatively is V over lambda. So that's what we've got in this. So if you were to tell me what sort of frequency the sound is, I could use that to calculate my wavelength or vice versa. Okay, so now let's look at the case where it's smaller. So we've got that source that's moving towards us. The apparent wavelength, and that's really what I'm saying when I say smaller lambda, that's the apparent wavelength. In this situation, that wavelength, well, it's going to be the original wavelength. So I'm going to just put here reg for lambda regular for the just, that's what we get. But then we're going to take away from it a certain amount. Well, how much we're going to take away, it depends on how fast that car is going. So I'm going to say that this thing's moving with a velocity of v sub s. So that's going to be source. That little s is going to be for the source. So this is the velocity of the source of the sound. And so what we need to do is we're going to take that normal regular wavelength, but we need to subtract off the distance that it traveled by the time that next one comes. Okay, well, the distance that it traveled is going to be the speed divided by the time, right? Good old, or sorry, speed times the time, so good old dirt. And so that's going to be the v sub s times its period. But period is 1 over frequency. So this is going to be our good old regular wavelength minus Vs over frequency. So let's replace that wavelength as V over F. And so what we see is 1 over the frequency times V minus Vs. Okay, so that's our new wavelength. Well, that's cool. But let's look at what that means in terms of its frequency. The frequency is V divided by this. And so what we're going to get in terms of the frequency, let me just write it right here. I just lost my blue pen. There's another one. So this is going to be the, let's call it F sub O. So this is the frequency of the observer. It's going to be V divided by this lambda. So if we just kind of flip that over, it's going to be V over V minus S, or V minus V sub S, times Fs. So let's box this. And again, the way to read this is that the Fs are the frequencies. The F sub O is the frequency of the observer, so us. The F sub S is the frequency of the car, the source of the car. And then V is the speed of sound, the speed of the wave, just generally. And then the V sub S, that's the speed of the source. All right, so cool. You buy that? So think about what's happening to that frequency. We're going to take V minus Vs. So that's going to be a smaller number. So that makes this bigger, which means we're increasing the frequency. So we're hearing it more often. Those waves are coming faster. All right, so let's go to the bigger lambda, the going away from us. So again, let's go with the V equals V sub S. We can kind of follow the exact same structure here, except now it's going to be that wavelength plus VST. So we're going to add to it, add to that distance, the distance traveled by our source. So that becomes a plus, this becomes a plus, this becomes a plus. So everything's going to look exactly the same, except we're going to find that the frequency of our observer is going to be V over V plus Vs. Okay, so when that source is moving away from us, it's pretty much the same. It's just in one case we're subtracting, in the other case we're adding. All right, well, this is if these are speeds. But what we're going to do is actually think of them as velocities. Because check this out. What's the difference in the velocities of these two cars when they're going away from us versus coming towards us?
If we think about it as vectors, probably 0.
Okay, so as vectors, the only difference, it's not their speeds, but their signs.
Mm-hmm.
One's plus and one's minus. Well, if we went with the going away from us as plus, the coming towards us would be a negative Vs, right? And look at what happens to this formula if it's V minus negative Vs. It actually looks exactly the same. So we don't really need to break them down into two different cases. You can just look at this one and go, oh, if it's moving away from us, it's V sub s is positive. If it's moving towards us, V sub s is negative. And it's the same formula. So I don't know if this book, I don't know which way this book does it. But some books will have it just as one formula. Sometimes they'll put like a plus or minus and say, you know, the plus is if it's moving away, minus if it's moving towards. I like just having one and just remembering that when we're talking about, you know, velocity, we need to know direction, and so we need plus or minus. So I'm actually going to look real quick. I've got a copy of the book here because I truly am curious what they do. Of course, that means I got to find Doppler effect. Ah, yes, they do the plus or minus. All right. Well, anyway, so they do plus or minus. Again, if they're moving towards you, it's a negative. And they're moving away from you, it's a plus. So however you want to remember it, doesn't really matter to me. But notice that it is kind of similar form. All right, so this is why as they go by you, you hear that change in frequency. Fun fact, if the observed frequency goes down, lower frequency means lower note, lower sound. So think about it, as that car goes by you, you hear the, oh, right? It starts higher pitch, goes lower. That's because it's gone past you and we're decreasing the frequency. We're spreading them out. All right, so this was stationary observer and moving source. But it turns out that you can also get the Doppler effect if the source is stationary and the observer is moving. So we're going to use the same kind of picture here, but this time we're going to have us be the ones moving. So again, we've got our waves set up here, but now let's start walking towards the source. All right, so let's give ourselves a velocity, and we're going to call it V sub O. So the speed or speed of the observer. And let's think about what's going to happen. Now, these waves Just think those waves as that's where they are. Okay, so they're not going to have a difference in wavelengths. But let's think about us as we walk towards it. Now, normally, if we were stationary, it would take a certain amount of time for that next wave front to hit us. By us walking towards it, we've decreased how long that takes. Yeah, you kind of buy that?
Yes.
So in this situation, it's going to appear to us that we have smaller lambda. Because the wave fronts are hitting us sooner. In the other case, if we start walking the other direction, now it takes longer for that next one to reach us because we're running away from it, basically. We're running away from that wave. It will catch us because we're not going to be able to go faster than the speed of sound. But it's going to take longer for it to reach us. So we see that as longer wavelength. Well, that's exactly what we saw before, right? But now what's causing that change in wavelength is actually the speed of us, the observer. So let's actually look at this from a frequency standpoint, because I think it might be a little bit easier. So frequency is V over lambda. So if we look in this first case where we've got the smaller lambda, normally our frequency would be V over lambda. But now we need to change that because we're going to increase the frequency. We're increasing it. It's going to happen more often. And that's going to be determined by our V sub O divided by lambda. All right, so if we do that, kind of run the numbers on it, we get F is equal to V plus V naught over lambda. The lambda, the original lambda, was V over the source frequency. And if we invert and multiply, we get that that's equal to V plus V naught over V times Fs. So we are seeing the frequency increase again, but it's coming from a slightly different way. Right before, we saw it with a decrease in the denominator of this fraction. In this case, we're seeing it as an increase in the numerator. Okay, well, for the other one here, I'm sure it's going to come as no surprise. All we got to do is make this a minus, because now we're walking away. So we're decreasing the frequency. That becomes a minus, that becomes a minus. And just like before, we get a very similar form. It's just one's plus and one's minus. So again, think of these as velocities, and it makes total sense. We're moving to the right here, so that's a positive velocity. That's just how it is. When we go to the left, we now have a negative velocity. Negative, negative is a plus. So you're going to get this same effect if you, as the observer, are moving, even if the source is stationary. All right, so then the next obvious question is, well, what if both are happening? What if we're moving and the source is moving at the same time? And it turns out that you can actually combine these nice and easily into one formula. And it looks a little bit like this. So now that we're done with our dude walking, let's just go ahead and combine these. So what you're going to see is that the frequency that we hear as an observer, so F sub O, it's going to equal V plus, I'll do it like the book, V plus or minus VO divided by V minus or plus VS times FS. And it's basically you just divide the one by the other, and those V's, they end up canceling. All right, so here's your Doppler effect formula. And I know that I kind of derived this talking about sound, but it doesn't have to be about sound. And as Bradley was asking earlier about using this for astronomy, you can do the same thing with light. It's just that C, or that V, is going to be the speed of light. So we call that C, 3 times 10 to the 8th meters per second. And of course, the frequencies we're going to use are a little bit different. The frequencies of light versus the frequencies of sound are off by orders of magnitude. But you can actually apply this to any kind of wave. Okay, so again, we need to remember what's what, right? What does this mean in terms of moving sources versus observers and all that? And so basically, here's how to remember what's going on with the top, with the observer. Okay, so if we have a moving observer, we really have two things, right? One is towards the source, and the other is away from the source. If we're moving towards the source, we're going to use plus. If we're moving away from the source, we're going to use minus. So that's this one on top. And then if we've got a moving source, again, the two choices are towards the observer and away from the observer. And here the roles are different. When it's towards, it's going to be a minus. And when it's away from, it's going to be a plus. That's this guy. Basically, just think about it this way. If we're going to decrease the wavelength, if we're going to run into these wavefronts faster, we need to make it a minus for this guy, right? Because we're making the bottom smaller. And then for the observer, it's the opposite, because we need to make that number on top bigger. So since it's a fraction, that's why it's reversed, the plus versus the minus. And then, of course, if one of them is stationary, it doesn't matter, because either that VO or that VS are constant, and they just go away. Okay, so let me show you how this is done. Let's actually do a problem so that we can calculate it, and this will also help us a little bit with the, is it a plus or is it a minus? Okay, so let's say that we're on the highway and a police officer is coming towards us with their siren going. So we're cruising down the highway. So this will be us. I'm going to put in O for observer. And let's say we're going down the highway here. And let's say that we're moving at 15 meters per second. So then from behind, we see the police officer. And so this is going to be our source. But they're hauling. They're going 45 meters per second. All right. The siren, let's say that it's blaring out a frequency of 300 hertz. What I want to know is, what frequency do we hear? What is F sub O? Okay, well, there's one other thing that we need in order to calculate this. We need to know what is the actual speed of this wave. So let's just make it a nice, easy number. Let's say that V is 340 meters per second. So it's always somewhere in that 330, 340 range. So let's just make a nice number, 340. Okay, so let's see if we can calculate this F sub O. So in terms of where everything is going to go, we're going to get 340 for our V. Our V sub O, that's us. We're moving at 15 meters per second. The V sub S is 45. And then we're going to multiply that by the actual frequency that's being produced. And you notice I didn't put pluses or minuses because we got to see if we can figure that out. So let's start with the V sub O. So V sub O, right now, are we moving towards or away from the source?
Away.
We're moving away. They're catching up, but we're definitely moving away from them. So what does that tell us to do on top? Plus or minus?
Plus. Okay, apparently minus.
Sure. Okay, so when the observer is moving away, that's the minus. So for the observer, this is going to be minus. Okay, so then what about the source? Is the source moving towards or away from us?
Towards.
It's moving towards us. So again, plus or minus?
Plus.
Are you sure?
Yeah, because it says moving source towards observer plus. You wrote that.
You sure?
I copied what you wrote down.
So it should be minus. This was the second set. I had two sets.
Yeah.
The one was the observer, the other one was.
Mm-hmm.
Because it should have been plus minus minus plus.
Plus minus minus plus.
Yeah.
Oh, maybe I'm just going dyslexic in my old age.
So.
Sorry, everyone.
That's okay. I got a couple people who got my back. Thanks, Victor and Caesar. I appreciate it. So it should be minus. Because as they're moving towards us, we need to have that frequency increasing. And honestly, this is where the issue is going to be with doing Doppler effect, is remembering, is it plus or is it minus? Okay, well, now we're ready to actually calculate what this new frequency is going to be. So if you take the difference, 340 minus 15, that's 325. We're going to divide that by 295, which is 340 minus 45. And then multiply that by the 300 hertz. And I get 330.5. So what we're going to hear is a sound that's higher pitched than the actual sound from that police car. So if that police car was stationary and we heard its siren, it would be much lower in pitch than what we're hearing right now. Okay, so now a little bit later, eventually this police car is going to get up to us and pass us. So let's look at the same situation, but now let's have that police car in front of us, but still going at the same speed. They've just have passed us. So now we're going to hear a different sound. And if we go to the formula in this case, again, we still have 340, 15, and 40. Like those things are all the same. And then we're going at, we got our 300 hertz. But again, is this plus or minus for each one of them? So now let's look at us, the observer. Are we moving towards or away from the source? Okay, so we're going towards it, which means now we need a plus on the top. The source is moving away from us. So since it's moving away from us, we need to put a plus down there as well. So let's see what this gives us. So if we add instead of subtracting for both of those numbers, we're now going to get 355 over 385. Again, we'll multiply that by the original 300 hertz. But now this is going to be 276 point something, 0.6. So it's going to be a lower frequency. So it all depends on how things are moving relative to each other. So to get back to Bradley's thing about doing this to look at stars and whatnot, we're doing exactly the same thing. And we use that to figure out what kind of velocities they have, whether they're moving towards us or away from us. Because we saw that there's a huge difference, right? Like in one case, the frequency went up. The other case, the frequency went down. And that's what we use to determine whether or not stars are moving away from us or towards us. All right, so this one, just be really careful, plus or minus, because like I said, that's going to be where you run into problems. But it's an apparent frequency. It's not that the waves have actually changed frequency. It just appears that they have because of the movement. It's the same kind of thing that like, you know how if you're in a bus or a train or something and you were to drop a ball, it looks like it just drops straight down. But someone outside would see it look like it fell forward. It's the same kind of thing. It's an observed difference, even though it's not really a difference. It's just different because of the fact that the two people watching that event are experiencing different things. It's the same thing here. It just appears that that frequency is different because of the fact that the observer and or the source are moving. All right, so there's Doppler effect. It's kind of cool. Now, this actually has a lot to do with what happens when we approach the speed of sound. Because just look at this formula, and let's say that that race car that was going by, or the ambulance, the police car that was going by, or whatever, what if they start getting close to the speed of sound? Kind of come back and look at this, where we had V plus or minus V naught. And let's go with this case. of they're coming towards us, but they're going closer and closer to the speed of sound. All right, so here we are as an observer. And since it doesn't really make sense to have a car going the speed of sound, we'll have an airplane going the speed of sound. So we got Chuck Yeager and his Bell X1 cruising at us. Okay, now, if they were going exactly the speed of sound, what would happen?
The observer
The
or the plane?
source. So we're stationary. Well, actually, let's just be stationary. So we're just standing there watching this plane come by. So what happens as V sub S gets closer and closer to V?
It goes to 0.
So the bottom of this goes to 0. So obviously it can't equal, so that's a problem. But as it gets closer and closer to it, this thing blows up, which means our frequency gets large. So as this plane's speed gets closer to V, the observed frequency goes towards infinity. And observed frequency, it's the reciprocal of our wavelength. And what we're seeing is that wavelength approaches 0. So those wavelengths are getting closer and closer and closer together. If that plane were actually going the speed of sound, exactly, the wavefronts would be on top of each other. Because every time it emits a new wave, it's caught up to the previous wave. So you remember how when I drew it before, there were these series of things coming out? If it was exactly V sub S equals V, what we would see is, here's wavelength number 1, wavelength number 2, number 3, 4, 5, 6, 7, 8, 9. And it would basically just create like a wall. Well, this is why it was thought that it was impossible to go past the speed of sound. At one point in time, historically, they thought that you were not going to be able to break the speed of sound because they knew that this pressure wave was getting built up and each one would add more to the pressure wave and you could never actually get past that pressure wave. Okay, well, we know that we can get past it, but interesting thing happens once we get past the speed of sound. So let me start drawing some waves to show you what's going on there. So here's going to be our plane. I'm going to start flying it the other direction because it'll be easier for me to draw it. Not the plane, but the waves. All right. So as it's flying in this direction, let's think about what happens. So it emits a sound. And so we get a sound wave that starts. Okay. So let's just do a little sound wave. Now, a little bit later, it wants to start making its next sound wave. So this one's going to expand whatever the wavelength is. So it's going to be concentric circle, but it's going to be a little bit larger. But now I need to draw another red circle. But this red circle needs to be centered at wherever the plane is. Since the plane is going faster than the sound, it's going to outpace this green. And so the new center is going to be somewhere beyond it. So let me draw a similar circle there. So this green one was the original wave. We're just now at the next stage of it. and the red one is the new wave. Okay, so some time goes on. We're going to get the next stage of this wave. So purple is step number 3. Well, this other red circle now has expanded to the green circle. But again, the plane has outflown the green circle, so there's going to be another red circle that's starting out here. So we kind of see this. So you're starting to see like a snowman, right? Red, green, purple. Well, let me do one more. I don't have enough space to draw it up here, so this will be in black, but let's pretend that it continues up there. So there's the black circle. We need a purple one around this green one. We need a green one around the red one. And then we need a red one that's out past the green one. So that's its new center. Something like that. I think that my black one got a little bit big down there. I'll try to rein that in a bit better. Okay, so do you kind of see what's going on? The colors, think of the colors as the starting, or they're the different phases of the wave. So the red circle is the start of each sound wave. Then green is the next stage in its evolution. Then purple, then black. But each time we're kind of running past the other one. And so what we end up getting, if we are to kind of compile all these sound fronts, or sound waves, there's going to be ones between the red and the green, right? I could have drawn a little blue one in here, which would then would have led to a little blue one here, or whatever. But if we continue doing that, what we end up seeing is a wave front that moves like this. Okay, so this is actually the wave front. And if we go 3-dimensional, remember that this is 3-dimensional. These are all spheres. So we're going to see the same thing, but out here and up above and rotating around. And eventually what we get is a cone. So when you pass the speed of sound, you actually start producing a wavefront that's conical. All right, well, when you get a sonic boom happening, what's happening is you've broken past this. You've broken past into this situation, and the sonic boom occurs along this conical wavefront. So I don't know if you've ever experienced one, like if you've ever been around somewhere where a plane has flown over you super fast, but that's a sonic boom. You also get sonic booms, mini sonic booms from like a whip. Like when a whip cracks, the end of it is moving faster than the speed of sound. So you get a little mini sonic boom, things like that. But anyway, it actually progresses on a conical wavefront. So it's also kind of interesting if you look at pictures of like planes that are going supersonic, you'll see clouds forming at the very nose of them. And that's because of that compression of the air, and it's causing all of that water vapor to condense and forms a little cloud. So it's kind of wild what happens when you exceed the speed of the wave. Now, we don't have something analogous with light because as far as we know, you cannot, well, you can't get past the speed of light. Turns out that mathematically we could be going faster than the speed of light as long as you don't try to slow down. But we can't get to this, so there is no such thing as a optical boom, right? An optic boom. But we have similar issues as we get closer to the speed of light, but that's a whole nother story for relativity. All right, so there's a little bit about sonic booms and why they show up and how they're affected. So you remember back when you learned about hyperbolas, and you were probably wondering, yeah, who cares about hyperbolas? Well, it turns out that if you were to look at locations on, say, on a plane, so like, let's say we're out in Kansas or something, and you were to look at all the places that experience a sonic boom at the same time, they're on a branch of a hyperbola because it's a conic section, right? As you slice through that cone, you get a hyperbola. Anyway, fun fact, tying back some of your math. All right. Well, I have one more thing I want to share with you. I want to talk a little bit more about interference. But actually, before I go there, any last questions? Or any questions, I should say. I want to talk a little bit more about interference real fast. Because we saw that waves interfere, and you know, it is what it is. It's not a good thing or a bad thing. It's a thing, right? But we have interference. But I do want to talk about a couple of things that happen with interference that are a little bit interesting. So we already saw that you can get constructive and destructive interference. And so the destructive, that's where the waves cancel each other out. And so in terms of sound, it's a dead spot, excuse me. And then constructive is where they build upon each other, and then we get louder spots. So hopefully you remember when I took the phone and I kind of walked around when I had those speakers going, you could actually tell places where it got louder or quieter, and that was the constructive versus destructive interference. Oh, so here's a fun one. You guys know noise canceling headphones, I'm sure. A lot of you might have them. They actually use destructive interference. What they do is they register what sound is coming in, and they really quickly produce a wave of the same frequency but out of phase so that they get destroyed. So there's a real application of destructive interference. But the thing I want to talk about is what happens when their frequencies aren't quite the same. Because we saw in order for them to cancel out, they had to have the exact same frequency. So if the frequencies are off a little bit, that means their omegas are off a little bit. So we'd have, say, y1 is equal to a cosine of omega 1t, and then y2 is equal to a cosine of omega 2t. And now when we combine them, we can't just slap them together. We actually have to use the sum to product formula for cosines. So that's one of those lovely trig forms that you saw once upon a time. But what ends up happening, I should have had the kx's as well. But when you combine these things, what you end up getting are two sine forms. There are two sinusoidal forms. One of them, well, let me just show you what you get. So you're going to get 2a times the cosine of f bar times t, and f bar, whenever I put a bar on top, I mean average. Okay, so this is your average frequency. So if you've got the two frequencies, you just average them. And then the other cosine has in it, again, 2 pi times the difference in their frequencies divided by 2 times t. Okay, so what this means in the real world. Again, the 2A, that's just telling you how loud it's going to be, right? Depends on the initial amplitude. But this piece right here, notice that it looks just like a wave, right? 2 pi f is the same as your omega. So what we're going to see here is a 2 pi f times t. This is going to be kind of your average sound. So that's the sound you're going to hear. But then this other cosine, what it's going to do is it causes an oscillation. And I'm going to put here in intensity. So it's changing how intense that sound is, and it's going to oscillate. And so there's kind of a new frequency here. And this frequency is that absolute value of the F2 minus F1. And this is what we call the beat frequency. And what you hear, and I will do this, well, I'll go mobile and take you over to where I've got the setup. What you're going to hear is a kind of a wobbling of the sound. Okay, we'll have a sound, right? We'll hear that buzzing, but within that buzz, we'll hear it kind of go wah, 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 right? So it's got a general sound level, but it's kind of oscillating. It's warbling, or however you want to say it. And that's what we call beats, right? That's a beat. And the beat frequency is really just the difference in the two. And like I had mentioned before, we use this when we do something like tune an instrument, because if our frequencies are close but not quite on, you can actually hear difference. Okay, so I'm going to change my earphones here real quick so that hopefully I can hear you guys. Can someone say something real fast for me?
Hello.
Hey, what's up?
Okay, cool. Gotcha. Thank you. All right, so we're going to go mobile. Let me take this camera. So, hi guys. Let me change the orientation on it. So it's not very exciting. I didn't actually move my table. You may have noticed that my space here is kind of on the small side, right? And I've got my workout bike, and there's the lab table, and so it's a big pain in the ass. I just went ahead and set this up down here on the ground. But what we got going for us is the same thing that we saw before. Hopefully you recognize these. These are the wave producers, wave generators. So they're going to create sinusoidal waves. I've got them hooked up to the separate mechanical vibrators, so speakers. So let me go ahead and turn them on. So hopefully you hear that. So that's 1,000 hertz coming off of one of the two speakers. It's actually this one over here. Now I'll go ahead and turn the other one on. Also at 1,000 hertz. So hopefully it just sounds louder, right? So these two are in exactly the same frequency. So we're getting nice even sound. Now I'm going to change one of them. Actually, I'm going to change both of them. I'm going to bring them down to, let's say, 200. So you should definitely hear two different sounds. because one's at 1,000 hertz, the other's at 200. But let me adjust the other one. Whoops, too far. Okay, so now they're both at 200. You just hear a lower sound than before. Okay, so now what I'm going to do is I'm going to change one of them. So what we have is 200 hertz and 201 hertz. So my question to you is, do you hear or feel kind of an oscillation of vibration within that 200 hertz? Let me change this one to 202. So do you guys hear that?
Yeah.
There's a okay, so right now the difference in these frequencies is 2 hertz because I've got 200 and 202. And if you concentrate on that little warbling and you were to like snap your fingers every time it happens, it's happening 2 times every second. Let me change this one back to 201. So maybe you can hear it again. I'm going to snap with it. But you notice that it slowed down to just once every second. Well, let me make it fractional. So now I've got 200 and 200.5. And so if you still hear it, because I can definitely still hear it, but I'm here, so I don't know how well it's translating. But that warbling is happening not nearly as frequently. So there we're back to 1 hertz difference. That's a 2 hertz difference. That's a 3 hertz difference. And pretty soon, that's 5 hertz difference. You can still barely catch it. This is a 10 hertz difference. And you can probably still feel it. Now we're at a 20 hertz difference, and it's getting hard to feel that beat. You can tell that they have different frequencies. The sounds are different, but it's hard to notice that beat difference. All right, well, mathematically, it must happen, right? We know that it must happen by the math, and it's really cool that we can actually hear it as well when we put it into play. All right. So, fun with sounds. But there you go. All right. So I don't actually have anything else I want to do today because we're kind of at a good stopping point. So let's just talk about what's going to happen tomorrow or Friday and stuff. So the next couple of days, here's what's going on.
We've got, first on Friday, we are going to do a lab. My intention is for us to do a lab regarding standing waves. So I believe I've got everything that'll work out. So we're going to go ahead and play with standing waves. There's not going to be a quiz. No quiz on Friday. I'm going to give you guys a break, especially since I haven't even graded the last one. So no quiz on Friday, but I am going to split you guys into 3 lab groups, and we'll do kind of the same thing. We'll start one group at 3, the next group at 3:45, and the third group at 4:30. So that way we'll be done earlier. I will post something with your lab groups on, I'll post a message on Canvas. And again, we'll see how the randomizer does. I'm just curious because I haven't really been paying attention. Have the groups changed? With a set of 9 or 10 of you, it won't seem like it changes much because you'll often have like 2 of the same people, but if nothing else, your time should change. It'd be really weird if everybody gets like, oh, I'm always in the first one. Anyway, so I'll randomly assign you guys into groups again, and I'll post that on Canvas. So Friday, no class or no lab, no quiz, only lab. So then Monday, we don't have class. Monday is Memorial Day. So if we were on campus, we wouldn't be meeting. Well, we're not going to meet virtually. So enjoy a day of not being in Zoom. And so the next day that we actually do anything new in terms of material will be on Wednesday. And we're going to hit the last section of this class. So the last section of this class is thermodynamics. Like I mentioned earlier, that's basically we're going to be looking at heat and how heat moves and the mechanisms thereof. And that will basically be our last. I think we've got 4 weeks left. So like this is flying by. I can't believe how fast class is going. But I think we've got like 4 more weeks and then a final. So we're definitely in the home stretch. So that's where we are. Do you guys have any further questions or comments before we call it a day?
I have one.
Okay, go for it.
Have you ever seen the movie Deja Vu with Denzel Washington?
I have not.
Okay. All right, then. I'm not going to spoil anything. You should really watch it. You would get a kick out of it.
Okay.
I think you'll enjoy it.
All right. And it has something, I'm sure, relevance to sound waves.
Just physics, really.
Okay. I will put it on my list. I probably won't get to it for quite some time, just to be perfectly honest. But I'll try to keep that in mind. Deja Vu.
Yeah, it was really good, and it was not what I expected, but I was very impressed.
All right. All right. Anything else?
No.
No?